Okay, guys, let me see if I can help out with the lab. Now, here's something you kind of have to understand. This lab is difficult if I'm there, and if I'm there trying to like keep you in bounds, and telling you, giving you hints and clues and things like that. You know, this is a difficult lab, let alone, trying to do it completely on your own. But keep in mind, I mean, what you've been doing is real science. I mean, you don't have anyone there telling you what or who knows what the answer is, and that's what real science is. And that's what's happening with the the coronavirus right now is we don't know what the answers are. People are just out there trying to research and figure stuff out and trying to figure it out from the data they collect. All right. And so this is what you've been doing. You've been doing some real science. And so what I'm going to do here is I'm going to kind of point you in the right direction so you can maybe start interpreting your data a little bit so you can kind of see, oh, how um, how does this do? So here's a couple of things you need to worry about or not worry about. The only things you really need to worry about, all right, are the heights that you measured. So this height here, h, right, and the distance here. So, the thing flew off and landed over here, and you measured that distance from the launch point to where it landed. Those two are the only two things you need to worry about. Okay. You do not need to worry about the acceleration. You do not need to worry about the time. Um, you don't have to worry about the mass of the stele or anything like that. Okay. Those are the only two numbers that matter. Now, why are those the only two numbers that matter? Well, I'm going to get into that here in a second. Okay. So the first thing we have to look at here is remember, we're talking about this is the law of conservation of energy. So we're trying to show that all of the energy doesn't go up or doesn't go down. That means at position one, it has the same amount of energy at position two. So position one is where you let go of the ball at the top of the track. Position two is where it got launched at the end of the track. Okay. And so what we're trying to prove is all the energy it has here at one, it's all the energy it has here at two. Okay. Now, at position one, what is its energy? Okay. Well, does it have any kinetic energy at position one? The answer is no, it does not. Because when you release it, it's not moving. So it's not moving, it's starting from rest. And so it has no kinetic energy to begin with because the velocity is zero to start. So that means all of the energy at one is from potential energy, which is this formula, mg and h. Okay? Now, when we get down here to 2, does it have kinetic energy? Absolutely. The ball is moving. And so it's 1/2 mv squared is how we would calculate its kinetic energy. But let's take a look at the potential energy. Does it have any potential energy? And the answer is no, it does not. All right? Because if we're measuring our height from the edge of the table, like we were here, all right, that height right here is 0. So at position 2, there is no height and there is no potential energy. Okay? Now, some of you might be thinking, yeah, but that's off the ground because the ball actually went flying off the ground. Yes, that's true, but because our basis for our height is the edge of the table, we have defined the table as 0. All right. This is 0. So this has 0 height. And then this height is what it is above that. All right. Now, when you take physics, we'll go through and prove and figure out why that is the way it is. But for now, you can just trust me, it works that way. Okay. So at position 1, it's all potential energy. At position 2, it's all kinetic energy. What we need to prove is that those two are the same. Okay? Now, that'd be real easy to do if we could calculate the velocity here, but we can't. All right? It's not easy to do. So instead, what we're doing is we are measuring the distance that the ball flies off the edge of the table. And we're using the distance as a bit of a stand-in for the velocity. No, you don't need to know this time. Okay, you do not need to know that time. And if you even tried to time it, like with a stopwatch on your phone or a stopwatch, you would get horribly inaccurate and unprecise data. And so you should not even try. All right. You would need a computer to measure it for you to get anything that's seemingly accurate. Okay. So don't even worry about it. All right. So what we're looking for here is just this distance. And like I said, we're using this as a stand-in for the velocity. This time never changes. All right. This time here will never, ever change no matter how fast it's moving. All right. So the faster the velocity, the faster the distance. So if we double the velocity, we will double the distance. If we triple the velocity, we will triple the distance because the time won't change. Okay? And that's all we really need. So back to where we're at here. Like I said, this distance is going to stand in for velocity. All right? It's just going to kind of take the place of it right now. So at position 1, all the energy is from the mass times gravity times the height. Now, at position 2, all of the energy comes from 1/2 the mass times the velocity squared. Now, what we want to look here is I made you do this multiple heights. And that's really the key, is that there are multiple heights. Because there are multiple heights, there will be multiple distances. And because there's multiple distances, remember the distance is a stand-in for the velocity. So that means there's multiple velocities as well. All right. So because we're changing the height, are we changing anything else? The answer is no, we are not. We are not changing the mass, and we cannot change gravity on Earth. All right. So all we're really changing is the height. And that's all that really matters. At position 2, because we changed the height, are we going to change this half? No, we're not changing that. We're also not going to change the mass because we're using the same stele every single time. So all we're changing is the velocity. But remember, in the equation, it's squared. All right. So, and remember, what stands in for the velocity is the distance. Okay. So, how do we start seeing the relationship? Okay. Here's how we start seeing the relationships. Okay. Now, you did this experiment at several different heights. We'll call that height 1, and we'll do height 2 because those are the two. So we'll do height 1 and height 2. All right. What I want you to do, all right, is I want you to take height 2 and compare it to height 1. So take h2 divided by h1 and see what you get. Okay? Now, if you thought this through, and we're kind of looking at the numbers a little bit, right? Hopefully you picked heights that when you divide them like this, they come out to a nice whole number. So ideally, this number that goes here should be like a 2, a 3, or a 4. If you used weird heights, like let's say for height 2, that was 17 centimeters, and height 1 was 12 centimeters, well, you're going to get some weird number here. And the ratio that you're going to, the relationship you're trying to see here is going to be very strange, and it's going to be hard to see. So that's key number 1. Height 2 and height 1 need to play well together. All right. So height 2 should probably be some multiple of height 1. All right. And make sure height 2 is bigger than height 1 in this case. All right. Now, what you'll want to do is you'll want to take distance 2 from height number 2 and divide by distance 1 and see what you get here. All right. Now, I'm going to go ahead and tell you right now that this number here and this number here will not equal each other. All right? They will not equal each other. You would think that they would if we're trying to prove that the energy here is equal to all of the energy here at 2. All right? But that's not what the math says it does. So what you need to do is you need to look at the equation. All right? And you need to look and see, does this number with the equation, right? And remember, the equation is 1/2 mv squared, right? For the kinetic energy. And for potential energy, it's mgh, all right? So what you need to look at is there a way, though, that there is a relationship between this number here and this number here? And is that relationship evident in the equations that I've given you? They should be. Because remember, what's going to happen here is all the energy at 1, at position 1, all the energy is mgh, which is equal to all the energy at 2, which is 1/2 mv squared. Remember, we don't have to worry about the mass, all right? We don't have to worry about those, all right? And the real reason we don't have to worry about those is because what we're going to really do when we do this is we're going to divide mg like this. So what ends up happening is they cancel. That's what ends up happening, all right? So this relationship that comes out like this, all right, comes out like this. Now remember, all we're doing is we're using the distance in place of velocity because we don't have a way to measure the velocity. So we'll get the same relationship, okay? We'll just use d for v. All right, so we'll plug our d's there and there and see what we get. All right. So doing that, can you find the mathematical relationship there that shows that yes, the energy actually does stay the same because it follows the math that it, or the